Welcome everyone. This is a presentation of the work Electric Field Effect on Spin Wave Spin Currents by Vittorio Basso and Patrizio Ansalone from l'Istituto Nazionale di Ricerca Metrologica in Torino, Italy. I am Vittorio Basso presenting. So, the aim of this work is to study electric field in effects on spin current in quite a general framework. So, to present our results, I will start from somehow quite general observations regarding the motion of particles in electromagnetism. So, let's start from a well-known and simple example. If we have an electric charge in motion in some electromagnetic field, and we look at the motion of this charge from the point of view of the kinetics. So if we want to define the total momentum of this charged particle in motion, we have not only to take the product mass times velocity, but we also have to add the fact that there is an electromagnetic field. So electromagnetic field gives a contribution to the momentum, which is called electromagnetic momentum. And in the case of charges, it is the product of the charge times the magnetic vector potential that gives a contribution to the total momentum. This is an important fact if, instead of a classical particle, we take a quantistic particle. Therefore, we describe the charge in terms of a wave function. If we do like that, we discover that the wave function will accumulate a certain phase. And this phase will be proportional to the integral over the part of the vector potential. This is quite a well-known result and is at the base of several effects in physics related to the wave natures of particles. For example, let's take the Aharonov-Bohm effect, a quite important effect in physics that tells that if I have a particle, for example an electron with charge, and this particle have a path which surround a certain region with magnetic field B, but the trajectory of the particle doesn't cross any region with B, so B is equal to 0 in the path of the particle, we have an accumulation of the phase the same, because the vector potential will be non-zero, and therefore there can be interference effects. This is the Aharonov-Bohm effect. So an effect that is often used in order to claim the reality of the vector potential A. We can do the same thing, for example, instead of taking an electron, by taking a Cooper pair. If we take a closed path, we discover that the magnetic flux, which is enclosed in the path, must be quantized, again for interference effect reasons. And therefore, we demonstrate the quantization of the magnetic flux with the formula written there. So this is very interesting, but what happens if instead of the charge we put a magnetic moment? Can we do the same? Well, not exactly the same, but we can write similar expressions. So also for the motion of a magnetic moment, we will have a change of the momentum. Again, not only mass times velocity, but we have a contribution that comes from electromagnetism. And this time it's not due to the vector potential, but it's due to the electric field. Why we have such term? Because essentially the electric field is defined in the laboratory frame. So you can imagine if the magnetic moment is traveling a certain velocity, it will see in its reference frame a magnetic field that is just due to the say relativity which is intrinsic to electromagnetism. The presence of that magnetic field changes the total momentum. Then let's do the same as before. So consider that the magnetic moment is described by a wave. This is typical for neutrons. Neutrons have a magnetic moment, and the description, quantistic description of a neutron, requires something like that. The accumulation of the phase is now proportional to the integral over the part of the product E external magnetic moment. If we do, for example, the experiment, or if we take the case in which there is a certain line which is positively charged, and we consider a part which is enclosing this line of charge, we get what is known as the Aharonov-Kasher effect, the interference, the accumulation of the phase of the neutron, for example, when it's enclosing this region with line charges. Similarly, one can define, one can get the quantization of a quantity, which is called the electric fluxoid. But what we are interested in here is that we have not only particles with magnetic moments that behave like waves, but we have waves, classical waves, that transport magnetic moments. And these waves are the spin waves. So let's take the same thing, but instead of a neutron with a magnetic moment, let's consider a magnon. So take a magnetic material with a magnetization mainly pointing along the z direction. Take the small oscillations of the magnetization, the spin waves. Take an electric field, consider the propagation as it's written there. So the spin waves propagate along y, the electric field is along x, and then make the quantization. The quanta of the spin waves are the magnons. The magnons have a certain amplitude, certain magnetic moment, which is essentially minus twice the magnetic moment, the elementary magnetic moment. Therefore, we have the same results. If we have an electric field, the phase of the magnon will be changed. There will be an accumulation of the phase of the magnon when the magnon travels in a transverse electric field. But as the magnons has a truly correspondent to a classical wave, this means that the dispersion relation is changed. Dispersion relation is displaced. It's displaced, for example, in the picture shown there, in the negative wave numbers. Well, as the magnon is just Landeggi factor times mu b, then the shift is just, the proportionality of the shift is proportional to the electric field, and the proportionality constant is just a constant related to fundamental constant, that is the gyromagnetic ratio for electrons and the velocity of light squared. So this factor is a constant. This is a very nice result, which in a sense generalize, or at least use a complete correspondence of the magnon with the particles. So magnon as a pseudo-particle. But our point is another one. So if we are able to demonstrate these results for a pseudo-particle like the magnon, can we derive the same result also for the classical waves? So the classical spin waves that can be derived from classical micromagnetism, therefore including also magnetostatic waves and so on and so on. This is a good question because it would show also a way to tune the phase of the spin waves in a quite general way, just by using this electromagnetic effect. So this is the method that we have used. To do that, to try to derive the result also for classical wave, we have used a Lagrangian approach of micromagnetics. Lagrangian approach was derived by Brown itself. So the point is the following. If we take the Lagrangian, a Lagrangian for the fields, as for a classical particle, we have the difference between the kinetic energy term and the potential energy term. So Brown has shown that if you take as a potential energy the micromagnetic energy, the usual one, so including exchange, anisotropy, the energy of the magnetostatic field, and the energy in the external applied field. and you take as kinetic energy the term which is written there, and then you compute the equation of motion, then you end up with the dynamic equation, which is exactly the precession equation written below. So the classical precession of micromagnetism, in which the effective field appears, exactly the same effective field of micromagnetism. This is everything. I mean, everything is clear. Maybe it's not necessary to go through a Lagrangian approach in order to write micromagnetism, but maybe it's important if we want to add the electric field effect, because in an electric field we have also the transport of a certain quantity. I mean, in micromagnetism, for example, we can have the transport of a certain quantity of magnetization with a certain group velocity in an electric field. Then we have to add another potential term. How to go quantitative? Well, take, for example, the linear spin waves. In that case, we can simplify much. The kinetic energy term, the group velocity can be computed just by the dispersion relation. The amplitude of the spin waves can be written down in the way they're written there. Therefore, the full Lagrangian will be the one written there. There will be an extra term due to the potential energy in the electric field. So our idea was the following. Can we write this new Lagrangian formally as the old one, which is the one written at the right-hand side, the ordinary one? Is it possible to find a transformation that brings the new Lagrangian in electric field to the old one? Well, this is possible if you redefine the derivative operator. So instead of making the derivative along for example, the phase along direction y, you have to take the derivative but just add a constant which depends on the electric field. If you make such a redefinition, then you can use the old Lagrangian, but the derivative operator will be different. But imagine that you have all the possible results of spin waves, including all dispersion relations. Then, having redefined the derivative, it means that the wave number will be shifted. And so we have derived our result that was initially just made by comparison between the magnon and the classical particles. If it holds for all kinds of thin waves, it means also holds for surface wave, for example, where the dispersion relation is those written there. Therefore, we should be able, for example, to measure such a shift. This is interesting because it means that, for example, the wave with Q equal to 0 is nothing else than uniform mode. If we put an electric field, the uniform mode will acquire a certain group velocity. And this because there is also a contribution to the total momentum, which is due to the electric field itself. And therefore, it should happen something like that. I will try to conclude and to go toward the end by just showing some experiments that it's possible to do to, let's say, to derive to measure these phase shifts or this phase change. In this experiment here, I have no time to go into the details, but please have a look at the paper there. They were able to measure very small phase shifts. For example, take some of these results, so the picture top left, and you will see that there is a certain phase which is increasing when they increase the electric field applied. Well, we are not able to really demonstrate the reality of our result for the specific experiment because this is just one contribution of several that are around. Therefore, one should distinguish between some electromagnetic and other source of diamond-like effect that can also contribute. So, in conclusion, we have derived that the transverse electric field contribute to accumulation of a phase. This accumulation is proportional to the electric field and the coefficient is just a constant. This constant is quite small, but it's something that is measurable. Then I suggest also to listen to the talk of Patrizia Salone, same conference, where we exploit the idea of redefining the space derivative. And Patrizia will show how this effect, if generalized, that gives rise can give rise to DMI effect and easy plane anisotropy in a ferromagnet. And with this, I thank you very much for your attention, and bye-bye.